Length contraction is a result of special relativity, the second postulate that the speed of light is constant. So in an earlier video we talked about coordinate transforms. So if we have Alice here in the K frame rather, and then we have Bob, and they both start at t equals 0, and Bob is moving to the right with a velocity v. And this is Bob. An event for Alice, and we said it happened at 1, is going to look different for the event at Bob. It's going to happen at a different location with respect to Bob. So in this coordinate transform called the Galilean transform, where you have x prime equals x minus vt. So in our example, we had the event happen at 1, and Bob is moving at 4 meters per second for 2 seconds. So according to Bob in the K primed frame, you're going to have the event happen at 1. This is according to Alice, as measured from Alice, minus v, we said 4 meters per second, and t is 2 seconds. So the event according to Bob is going to happen at minus 7, which is way over here in the negative portion for Bob, in the negative part of his number line. Now, we also talked about how to account for the speed of light being constant. We have to include the gamma function, which looks like a square root of 1 minus v squared over c squared in the denominator. This portion here, 1 over that is the gamma factor. And with that, we have solved the fact that the speed of light is constant for all observers. Now, well, in all inertial reference frames. So at this point, we can take this concept of two events happening and expand that to the length of bodies. So we're going to take from Bob's perspective, we have x prime minus x prime left. The right hand side of the measuring stick here, and this is the left hand side of the measuring stick. This is both for Bob. What is this really? Okay, we're Bob. That's what we're talking about. This is the actual length of the measuring stick because we're holding the measuring stick. We can look at it and it's 1 meter long. This is called the proper length, and you can think of that as the length of something when you're holding it, when it has no relative motion to you. And we're measuring the length of Alice's measuring stick. So these two events, x sub r minus x sub L minus and v t1 minus t0. Alright, so here we're going to make the assumption that the two times that these are measured simultaneously, and this is tough to get away with in special relativity because the idea of simultaneity is also becomes relative, which we'll talk about later, but we're going to say our measuring sticks are pretty much right next to each other. And so that this term, t1, equals approximately t2, and this term goes to 0. Okay, so remember we said that this is the proper length, and this is often denoted by the subscript 0. L sub 0 is the proper length of this. This is the gamma function. Remember, it is this guy right here, and gamma function makes the overall number it is attached to bigger. This is the length we measure for Alice. So we are looking out at Alice and we're looking at the length of her measuring stick. So the proper length equals gamma times the length we measure for the other body that's moving relative to us. So think about what this equation means. Remember that for moving at 0.866 the speed of light, we have a gamma factor of 2. So if we measure Alice's stick having a length of 0.5 meters times gamma, our own stick is 1 meter. If we measure her stick being a length of 2 meters, our own stick will be 4 meters, etc. Basically what this equation means, at least for a gamma factor of 2, is that her length will always be half of ours. In other words, moving objects contract. If you have a velocity with respect to another body, what you see contracts. And this gamma factor makes it so you can kind of think about that. And this effect, the length contraction, happens hand in hand with the time dilation. These two effects happen together, and that's why it's referred to space-time. So it looks like I already shrunk the Roadrunner from a previous video attempt. But normally in the Galilean transform, this is what the Roadrunner would look like. But because we have length contraction, this is how we see the Roadrunner. You shrink it. So it's moving from left to right. And remember, we talked how time also slows down for objects in motion. So we see the Roadrunner. It's going really fast, right? The heart should be beating fast because it's going 86% the speed of light. But what we see from this shrunk down Roadrunner, we see it shrunk down and we see its heart going slow. Thump, 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 thump. All right, so by the time it takes to get to this little cactus, we had 5 thumps. Now what does the Roadrunner see? And remember that these effects are symmetric. I see him shrunk, but he sees the entire world shrunk. This is what the Roadrunner sees. He has the proper length. According to him, he's the normal size, and according to him, he's going at the normal space. Normal speed, normal time speed. Clocks run normal to him, and everybody's normal to himself. He sees thump, 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 normal heartbeat. 5 heartbeats to get from here to here. And from this reference frame, 5 heartbeats to get from here to here. So these space contraction and time dilation kind of work together to, make everything work out, and yet still the speed of light is constant in both reference frames. That's a bit confusing, but there's 2 ways of looking at it. And so, well, no, it's not 2 ways of looking at it. It's 2 ways things actually are. And it's not intuitive to us because we spend our entire lives at such low speeds. But these kind of relative, things being relative is actually a common thing. Like, just because the airplane is moving fast relative to you doesn't mean that the airplane is moving fast relative to the pilot of the airplane, and it's the same thing here, but extended into space and time. So here, he doesn't have to go very far, and time runs normally for him. For here, it just seems like he does have to go far, but time is slowed down for him, and they work together, mesh together to make this weird contraction and dilation seamless. The one kind of cool thing about it is if the Roadrunner is going fast enough, to him it seems like he doesn't have to go as far, so he doesn't get very much older going from here to here. So if you wanted to go to Alpha Centauri and you were somehow able to go 0.866 the speed of light, it would take you half as long because the distance between our star and Alpha Centauri would shrink and you could get there quicker. You wouldn't have to bring as much food, which is pretty cool. According to everybody on Earth, it would take you just as long. You would just be in kind of a molasses-like stasis. But, like I said, these 2 effects, time dilation, length contraction, they can't happen apart from each other. They're interdependent, and they work together to make it all fit together. It's pretty cool. So, thanks for watching.